Alrighty. Well, here we go. We're gonna try this. So let's just get started. We're gonna go to the polynomial remainder theorem because this is in place of Thursday's class connect. It's gonna be shorter. And hide this. Please make sure you've taken the readiness checkpoint. It sets up the course to support you guys. But we're going to always click on level activity because that's the goal. If not, just go back and hit that support level activity, okay? So look, they have our book for us. This is excellent. It's always nice because they'll take you right to what we're going to talk about. So we're actually going to use our book real quick and then we'll go back and solve some of the problems. But I want to talk to you about a few different options. So arrow back if you need to review about polynomial long division or synthetic division, because we're still going to be using that today, but mostly we're going to be talking about a different way to think about functions because I think it's very important. Okay, the theorem, and hopefully there it goes. The theorem is just stating that if you have a polynomial, the dividend, and you're dividing it by this, the x minus a, the divisor, and then you get the quotient plus the remainder is actually what the original dividend, the original function, would be equal to if you substituted a. See that a, that would be a real number, not a letter, it'd be a real number, back into the original function. That's what would be the remainder. The remainder would be equal to that. So this is really useful with complicated polynomials when sometimes actually dividing by this x minus a is easier to solve than substituting an a. There's other reasons too, but for right now, that's kind of the big idea. And this is why it works. This is, somebody saw this relationship that, hey, wait a minute, if I just substituted a into the polynomial, that would make this, right, the x minus a equal to 0. So then you'd get 0 times the quotient plus r of a, whatever the remainder is, and that is what p of a would equal. So sometimes it's a real number, sometimes the remainder will still be a function, but it'll be a much simpler function than the original one. Anyway, that's the thinking part. That's what they're doing. That's what they're talking about here. But the basic idea of the questions is they're going to ask you to use this theorem to find the remainder to solve for the original polynomial, the original function at that point, at a. So let's go see what that means when we're talking about it mathematically. So take a look. Use the polynomial remainder theorem to evaluate the polynomial for the given value. Function notation is something that's very important, so I want to talk about it a little bit. This is saying h of t, so it's not saying h times t, nothing to do with h, it's just the name of the function. The input value is t. So when you see h parentheses 3, it's saying t is equal to 3. Okay, that's all this is saying. And then the h of 3 equals is just our output. We just use it notationally, and I know, I'm sorry, you guys. We just use that to say, hey, we're evaluating this function at 3, instead of having a separate line where we said when t equals 3, h equals this. So now I just substitute this in. This is not using the polynomial remainder theorem. This is just another way to find that value, t 3 squared plus 3 times 3 minus 9. So that's 9. It should just be 9. Notice, because 3 squared is 9, 3 times 3 is 9 minus 9, so we're just left with 9. But again, you could use a calculator if you needed to. Okay, so I'm going to clear the screen. I can type in 9, and we'll get it correct. Let me move you up here. Yay! But that's not using the polynomial remainder theorem. We directly evaluated that function. We substituted t, we substituted 3 in where we saw t, and then we performed the operations. That is not using the polynomial remainder theorem. So let me show you what they mean about that. If, right down there, so if they wanted you, like, say, to show your work, we would take, and I like synthetic division, you can, especially when it's simple like this, 3, right? So if x minus 3, so we're going to make it a 3, right? X minus a is the condition for synthetic division. Then we write the coefficients, which would be 1, 3, and -9. Then we bring down the 1, and we start our process. I'll use that line as our line. 3 times 1 is 3. Then you add, right? 3 plus 3 is 6. Then you get 3 times 6, which is 18. Then you get -9 add plus positive 18. You're left with 9 as your remainder. Because remember, you have to do that step down in degree. So the final answer, if we wrote it as a polynomial, would be x. See, that's x plus 6 with a remainder of 9 over x minus 3, right? So that's kind of the final step when we do this polynomial remainder theorem. But you can always check your work by substituting it into the original equation and saying, oh, we found the value. Okay? All right, clear screen. Let me scroll down. So here's their synthetic division. So h of 3 equals 9. All right. So let me know if you have any questions about that, but good job. We're going to keep going. We're only going to do a couple more, and you can always check your work. So let's see. So parabolas and quadratic equations are very useful for modeling, like, our, things thrown, projectile motion. So let's see. A tennis ball thrown in the air, initial velocity of 20 feet per second, the height after t seconds is modeled by the polynomial where h of t is the height in feet, ignoring air resistance. So that's always a key concept because there's a whole nother complicated equations when you start to model this stuff for real. So just remember that as you're learning algebra, they're giving you the initial ideas, and then as you continue your lives, if you pursue a career, you're going to get more and more complicated equations, and that's okay. They'll be hard to learn at first, but then you'll understand. So just keep asking those questions, and remember, you can learn this. So if you're interested in the maths and sciences and the engineering, don't give up. Okay? All right. What's the height of the tennis ball after half a second? Well, notice its height in terms of t seconds is modeled by this polynomial. So that's a useful function for a real life situation. You would just substitute that in. If you wanted to do the polynomial remainder theorem, then again, you would do the synthetic division where you would just do a half. So I'm just going to do 0.5. Let's see if this works. Oh, sorry about my mouse work right now. Then you write the coefficients. So you get -16, 20, 5. Let's bring down the -16. Oh gosh, that's a -16. Sorry guys, -16. Here's our line. Now 1/2, 0.5 is a half, 5/10 times -16 should be -8. Oh boy. That's an 8. 20 minus 8, or adding or combining it, would be 12. This doesn't seem right. Oh, a half times 12. Oh no, that's going to be fine. Okay. Because I can kind of see about where the final answer should be. So 5 plus 6 is 11. Remember, this is our remainder. So often, I guess, it would be safe to say, I wonder if this is always true, that the final number If it's not 0, then it's our remainder. What if that's always true? I mean, I have to really think about it. If there's a rule, like in your book, you read that, oh, the last number is always the remainder, that's great. But why? What's happening there? So anyway, let's type in 11 and see if we did it. So notice that was synthetic division. I like synthetic division a little bit more than polynomial long division. It's just a simpler method. It's more efficient. But let's see if it worked. Cool. That's how you use the polynomial remainder theorem to evaluate functions at a value. So instead of substituting again in for t, you could do half a second in there. So half a second squared is a quarter. A quarter of negative 16 is negative 4. You can use a calculator. So we have negative 4, and then half of 20 is 10. So negative 4 plus positive 10 is 6. And then 6 plus 5 is 11. So always check your work. All right, so again, we could use polynomial remainder theorem, but right now, let's just plug this in using a calculator or our mind, right? Let's just substitute the value in, because sometimes in math, it's great to practice things, definitely practice it, but there's also, this isn't a very complicated function. So f of negative 5 means we're going to have negative 5 cubed, so negative 5 times negative 5 is positive 25. Positive 25 times negative 5 should be negative 125. We'll have negative 125 plus positive 25, because negative 5 squared, you got to use the parentheses. Okay. Then you would have negative 2 times negative 5. So you'd have positive 10, and then that's the constant term. That final negative 5 is the constant term. So let's see if this is nice for us. Let's see, a negative 125 plus 25, well, that becomes negative 100. Positive 10 minus 5 just becomes positive 5. So this should be equal to 95. And if not, that's okay. What did we do? Negative 125, positive 25 is negative 100, positive 10 is negative 90, and then negative. I'm silly, but look what I forgot. I forgot the negative. Let's try it now. Aha, we did it. And then come down here and you can see how they did the synthetic division. See how they set it up? Coefficient of 1, 1, negative 2, negative 5. Then down here, they have they want to evaluate it at, yeah, it clicks. I mean, why aren't you highlighting it for me? Ugh. Oh well. Okay. And yeah. So the rest of these, let me see if there's anything else. You can use the polynomial remainder theorem to try this out. That looks pretty good. That looks excellent, nice, good. Ooh, word problem. So we'll talk about that one in a second. Okay, so let's talk about 7 since it's a word problem, but the rest, try them, see what you get, see if you can do polynomial long division, see if the remainder theorem makes sense to you. Check it by substituting in the value in the original function. So the distance in kilometers from an earthquake's epicenter that a seismic wave can be felt is X minutes after the earthquake occurs can be modeled by this function. That's important, right? Actually, weather has a lot of math in it, a lot of math. And it's great. So, all right, what is the distance of the seismic wave felt 2 minutes after the earthquake occurs? So you could substitute 2 in wherever you see X and use your calculator, or let's see if it's actually faster if we do the polynomial synthetic division. I like the synthetic division. So 2 minutes, X minutes, so I'm going to write 2. And then I'm going to just write 1, negative 17, 160, negative 21, 293. So let's see if this is actually, 290, 93. Sorry for the mess, but let's do this. So you draw your line, you bring down the first coefficient, which is 1. Now you do 2 times 1 is 2. Then you add. So we get negative 15, right? 2 times negative 15 is negative 30. So we should get positive 130. Then 2 times 130 is 260, positive, minus 21, so it should be 239. Again, you can use a calculator. 239. Now 2 times 239 is, and this is 293, so hold on. 8, carry the 1, 6, 7, 4, 7, 8. And then now finally it's 11, carry 7, carry 7, 7, 1. If I did everything right, I can check. We'll check in a second. So there's that. I'm going to take a screenshot because it's going to disappear on me. And I want to be able to check my work because checking my work is how we learn. Even me. I make mistakes. We all make mistakes. Okay, you're so slow. Cool. So now we at least have that for if I need it. And I already forgot what the answer was. I think it was 771. Let's see. Woo! We didn't need to check our work because we got it correct, which means that we understand, we're ready to go, we're getting great practice. Practice is how you learn. You have to practice. So thanks for watching, and I'll see you guys soon. So